I am going to start my lecture today. I apologize not being able to be with you in Rome because I just got positive to COVID a few days ago, and so I am not allowed to travel. So I give my lecture by Zoom, and I hope that next week I will be again with you. I will talk today about, I will continue today to discuss the experiments on magnetic resonance and on lasers, which were started in the 20th century. What I said last week is that during the first year between 1920 and 1950, microwaves and visible light were mainly used to do some spectroscopic experiment. I talked in particular about magnetic resonance, and spectroscopists got a lot of information about the perturbation of spectral line by magnetic and electric fields, and also by the vacuum fluctuation. And I talked about the lamp shift and the anomalous magnetic moment of the electron. Then, starting in the 1950s, novel methods have been developed not only to investigate spectroscopically atoms, but in order to manipulate the atoms, to modify their property, and to prepare them in non-equilibrium states. And the first of this method was called double resonance, and the next one was optical pumping. And these experiments are exploiting the exchange of angular momentum between light and matter in order to orient nuclei and electronic magnetism in gases, providing very important information about the interaction between atoms and their environment. And these experiments led to the invention of the laser, which produce light with very characteristic features which are very different from classical light. So in this lecture, I will describe the main properties. I will describe the laser and the main properties of its light. I will insist on the monochromaticity, the spatiotemporal coherence of laser light, and explain how these new features have made possible to manipulate atoms and to achieve unprecedented precision in spectroscopy. I will also insist on the fact that laser light can concentrate a huge amount of energy in a very small surface and in a very short time. And this leads to strong nonlinear effects in quantum optics, and also to the possibility to make experiments which are called extreme light experiments. And so I will present orders of magnitude of achievable light intensities and pulse light duration. And I will discuss the new physics, which is now open to research. But I want to, since we are at La Sapienza, I want to start by a paper which was published in 1925 by Fermi and Rasetti. At that time, they were young, they were just getting out of the Scuola Normale di Pisa, and they were working in Florence. And they made a very interesting experiment in which they showed that the polarization of the light, which is of the fluorescence light, which is emitted by mercury atoms after excitation by a lamp, this polarization depends upon the magnetic field. And these experiments are really the precursors of the double resonance method, which was started only 25 years later. In fact, Fermi and Rasetti had a very simple and very crude experimental setup. It was a time when microwave spectroscopy was still in its infancy. And it is only in 1950 that the development of technology has made experiments possible. But nevertheless, Fermi and Rasetti had really started the field by making an interesting experiment. So you see the title, Effect of an Alternating Magnetic Field on the Polarization of the Resonance Light of Mercury. And you see here the picture that you have in the Aula Magna, which shows Fermi and Rasetti and his colleagues Segre and Amaldi. So what is double resonance? The double resonance experiment is a very simple one, which was invented by Kastler and Brossel in 1950. And I show you here the experimental setup. In fact, it's a magnetic resonance experiment. And the medium is a gas, which is contained in a cell that you can see here. There is a magnetic field which is applied to the gas, and a lamp which excites the gas on the side. And I can explain what happens in a very simple configuration where the ground state has an angular momentum g equals 0, and the excited state has an angular momentum equal to 1, which is split in the magnetic field into three magnetic sublevels with m equal -1, 0, and +1. And the interaction between light and the atom obeys to the rule of angular momentum conservation. For instance, if you excite from the ground state with a pi polarization, that is a polarization which is parallel to the magnetic field, this light carries 0 angular momentum along B0, which means that the only transition which is possible is a transition from Jg equals 0 in the ground state to the m equals 0 state in the excited manifold. If, on the other hand, you excite with sigma plus polarized light, each photon carries 1 unit of angular momentum, and the transition occurs between the ground state and the excited state with m equal +1. So the idea of the experiment is very simple. You apply on top of the static magnetic field, you apply a rotating field, B1 of t, which does magnetic resonance, which induces magnetic resonance phenomenon. When this field rotates at the Larmor frequency imposed by the static magnetic field, transitions occur between m equals 0 and m equal 1, and m equals 0 and m equal -1. So assume that you excite with a pi polarized light. When the atoms are resonant, some atoms are carried from m equals 0 to m equal +1, and when they fall back in the ground state, they emit sigma plus polarized photons. These photons do not exist if you don't have the resonance condition, because there is no possibility to emit sigma plus light along the direction of the static magnetic field. So if you use a detector here, you will see a resonance signal, resonance in fluorescence, when you will excite with a pi polarization and have a rotating field at the frequency of the Larmor precession. This is a magnetic resonance experiment with very interesting features. First of all, the population difference is produced by light. It's light which excites the atom in this state and not in the state +1 and -1. So you have a big population imbalance, which is not the case in the magnetic resonance experiment I described last week. Last week, the population difference was only due to the Boltzmann factor, and it was a very small difference at ordinary temperature and magnetic field strength. Here, you can have a huge difference in population because the light selects only one magnetic sublevel. So this is the first advantage. The second advantage is that you detect the resonance by optical photons. Optical photons appear only when you hit the resonance condition. In the magnetic resonance experiment I described to you last week, the signal was due to the spinning spins, and they emitted radio frequencies which were detected by coils, and the detection in a vapor or in a gas is very weak in this case. Whereas if you detect photons, the photons have a huge energy compared to microwaves, and the sensitivity of the optical detection is very, very high. So you get very beautiful signals. You see here the kind of signals that Brossel and Kastler obtained. This is the fluorescence in sigma plus polarization as you scan the magnetic field around the value corresponding to the resonance. You see that you have a beautiful Lorentzian shape, and if the intensity of the field, of the radio frequency field becomes large enough, you have a change in shape. You see that the signal reverse, you have a dip at the top of the resonance. This is called a Majorana resonance. And in fact, so I am describing here the work of Ettore Majorana, who was also one of the Fermi boys at that time. He studied the shape of the magnetic resonance signals when they occur on a spin 1 and not on a spin 1/2. Here you see that the resonance does not involve only 2 levels, but 3 levels. And in this case, you have interference phenomena, which shows that the probability to flip from 0 to +1 has a dip in the middle. What happens is that the atoms can either absorb 1 sigma plus radio frequency photon or emit by stimulated emission towards m equal -1 and then absorb 2 photons. So it's a 3-photon process which interferes with 1-photon process, and this gives the reversal of the signal at resonance. So I don't want to enter too much into these details, but I want to say that this kind of double resonance experiment have become very, very useful to get information about excited state of atoms, to measure the Zeeman effect, to measure the effect of electric fields, to measure the effect of all kinds of perturbation acting on the system. And more importantly, it led in a few months later to the development of the optical pumping method. Optical pumping is similar to double resonance, except that it occurs in the ground state of atoms. It's an orientation of the spin of atoms in the ground state induced by circularly polarized light. You see here the simplest case is the one corresponding to a transition between a spin 1/2 in the ground state and a spin 1/2 in the excited state. And you see immediately, I call n minus and n plus the number of atoms in the m equal -1/2 and m equal +1 state. If you excite this atom with circularly polarized light, the conservation of angular momentum means that you can only go from the -1/2 state in the ground state to the +1/2 state in the excited state, whose population I call NE. Once the atom is in the excited state, he falls back by spontaneous emission 2/3 of the time towards the n equal the n minus state, and 1/3 of the time to the m equal +1/2 state. So you see that after one cycle of absorption and spontaneous emission, 1/3 of the atoms are brought into the +1/2 level. And after a few cycles, all the atoms will end up into the +1 state. The system behaves as a kind of leaky pump, which pumps optically the atoms from the m equal -1/2 to the m equal +1/2 state. So it's a very simple process. It is based on the conservation of angular momentum during the absorption and remission of light by atoms, and it allows to orient the ground state of atom with a very large efficiency. And on the next slide, I give you all the equations which allow you to compute this phenomenon. You have three populations which are coupled together, n minus and n plus, which has a population of the m equal -1/2 and m equal +1/2 in the ground state, and NE, which is the population in the excited state. And the block equation, which describes the dynamical coupling of this level, is quite simple. For instance, the derivative of NE, the rate at which the excited state is populated, is proportional to the pumping rate, 1/Tp, times the population in n minus. This describes this process. And then you have a negative term, which describes the decay with rate gamma from the excited state down to the ground state. In the same way, you can write dn minus over dt, like -1/Tp n minus. This is the departure from n minus due to absorption of light, plus 2 gamma over 3, corresponding to the atom coming back to the m equal -1/2 state. And the last equation is also very simple to understand. Now, usually what happens is that the rate at which the atoms are excited by classical lamps is very small compared to the spontaneous emission rate. In other words, gamma Tp is very small compared to 1. This means that the excited state decays much faster than it is prepared by the optical excitation, which means that the population of the excited state remains very small compared to the population of the ground state n plus n minus throughout the process. So you can do a very simple calculation. First, you can eliminate, for instance, you can eliminate the excited state population by combining these two equations, and you get the equation which I show you here. And once you have do that, you can also remark that if NE is very small compared to n plus and n minus, the rate at which n minus and n plus evolves are opposite. dn minus over dt is equal to minus dn plus over dt, because the sum of these two populations remains almost equal to the total number of atoms. So when you do this substitution, you find that dn plus over dt is equal to minus dn minus over dt equal to 1/3, 1/3 Tp n minus, which means that the population of the n minus state decays exponentially with the rate 1/3 Tp, and the population of the n plus state increases exponentially. So it's really a pump which takes atoms from n equal minus and puts them into the n equal plus state. And here I have only considered these processes. I have neglected other causes of relaxation other than the one which are due to the optical pumping and spontaneous emission. So on the next slide, I show you the kind of signals that you get. You see on the left, you have a cell which contains atoms. Their spin are oriented in all kinds of directions. There is no orientation at the beginning. The Boltzmann factor is such that you have approximately equal number of atoms pointing in one direction than in the opposite one. And you excite these atoms with circularly polarized light, which carry 1 unit of angular momentum per photon. And after a time which is large compared to TP, all the atoms are oriented in the direction of the angular momentum of the photon. So you have oriented all your spins in a given direction. How do you detect this orientation? You just have to look at the transmitted light. If the atoms, and I come back to the previous slide, you see that if the atoms are all pumped in N+, N+ cannot absorb light anymore. The only state which can absorb light is the M equal -1/2 state. So once light is oriented, the transmission of light is maximum. All the light is transmitted. And if on the other hand, you look at the fluorescence light, the light which is emitted by the sample on the side, it is the opposite. The fluorescence light decreases and vanishes when the cell is completely oriented. So you see that you can follow the progression of the dynamics of the pumping by just measuring the transmitted and the fluorescence light of the cell. And you see here how the population of the N+ and - state evolve with time. The N- population tends toward 1, and the N+ population tends toward 1, and the N- population tends toward 0. So you see again that in this experiment, light plays a double role. It orients the spins, and the transmitted or fluorescence light is used to detect the amount of orientation that you have got in the sample. I show you here a very simple and beautiful experiment you can do once you have oriented your sample. You see here the cell. You have circularly polarized light coming inside, orienting the atoms along this direction, and then you detect the transmission light. And you have coils here which produce a transverse magnetic field. And what you do is that you start by pumping the atoms in 0 field, and then suddenly at some time you switch on a field B0. What happens is that the spins that you have oriented along the horizontal axis start to precess, and by precessing they go alternatively along the plus and the minus direction along the pumping beam, which means that alternatively the transmitted light gets fully transmitted or absorbed, fully transmitted and absorbed. And what you see is a beautiful damped sine curve, which occurs at the Larmor precession frequency in the field B0. So if you change B0, you will change the frequency of this phenomenon. And you have also a damping, which is due to the fact that atoms are colliding with the walls of the cell and colliding between themselves and losing at some time their polarization. So you can do a lot of static or dynamical experiment and study how spins which are manipulated by light evolve. And a lot of experiments have been performed in the 1950s and 60s using this setup. It was a time when I was doing my own thesis at the laboratory of Kastler and Brussels in Paris. And I describe you here the first experiment I did. You see on the left here, just the sketch of optical pumping setup. You pump with circularly polarized light. You just pump with circularly polarized light along the direction of the magnetic field. And you apply also a rotating field, B1 of T, which induced a magnetic resonance between the plus and minus state along B0. And this field, in fact, can be either a rotating field, in which case you get one resonance when omega is equal to omega naught, when the frequency of the radio frequency is equal to the Larmor precession frequency. But you can also excite your gas with a linearly polarized light, B1 cosine omega t, which just oscillates back and forth instead of rotating. And now it's quite clear that an oscillation along the x-axis can be decomposed into two opposite circular motions. This is the sum of a sigma plus and a sigma minus microwave, which are rotating, counter-rotating around B0. And in this case, what you expect to see are new resonances. And I show you here what happens. in the case of a circularly polarized microwave, like B1 of T rotating like that, you just get the absorption of one photon, sigma plus polarized photon, brings the atom from the -1/2 to the +1/2 state, in the ground state now. So this is just the ordinary magnetic resonance. But now, if the field is linearly polarized, you can also, on top of this resonance, have another one in which you absorb 2 sigma plus polarized photons, corresponding to rotation in one sense, and 1 circularly polarized photon in the opposite direction. So the angular momentum is changed by +1. And of course, the energy of this photon has to be 1/3 of the energy of the transition between the levels to conserve energy. You can also have a 5-photon transition by absorbing 3 sigma plus polarized photons and 2 sigma minus ones. And so I did the experiment by just pumping the atoms with circularly polarized light and looking at the fluorescence as I was tuning the magnetic field across the values omega naught, omega 0 equal omega, omega 0 equal 3 omega, omega 0 equal 5 omega. And you see here that indeed you have a 1-photon transition here, the 3-photon transition here, 5-photon here, 7-photon here, and you can even guess that you have a 9-photon transition here. You see that in order to see the multi-photon transition, you have to increase the intensity of the radio frequency. It's a very low frequency, 60 Hertz only. And you see another phenomenon which occurs as you increase the power, these resonances are shifted. They occur at smaller and smaller values of the static magnetic field. This shift is well understood theoretically. It's called the Bloch-Seeger shift. Bloch is again the guy that we have been talking about in the previous lectures. And you see that you can indeed induce these transitions by doing a very simple experiment. And this was, as I said, the first experiment in optical pumping that I did in 1965. So let's now look at another experiment that you can do with optical pumping. This is what I call the zero field resonance in transverse pumping, and it's called the Handler effect. So the setup is again similar to the previous one. You have a cell containing atoms, you pump them along the horizontal direction, and you first assume that you are in zero magnetic field. In fact, you will apply a magnetic field in the third direction, perpendicular to the plane of the figure. If the field is 0, the pumping will prepare the spins along the direction of the light, and after some time, the cell will become completely transparent. You will have no absorption anymore because all the atoms will be pumped in the level which cannot absorb light. Then you start applying a small magnetic field in the transverse direction, and you look at what happens. And in fact, what we see is that the transmission of the light along the x direction increases. What happens? In fact, the optical pumping is, in fact, there is a competition between the optical pumping, which tends to maintain the atoms along the x-axis, and the Larmor precession, which tends to make the spins fan out in the x or y plane and go around in this plane. And you see that if the magnetic field is such that you can have a large Larmor precession angle during the pumping time Tp, then the spin will be reduced, the average value of the spin will be reduced, and you will have more absorption of the light along the sigma plus direction. So what you see in this case, and I just show you the signal here at the bottom, you see a resonance around zero field. At exact zero field, you have a high transmission of light, and as soon as you depart from zero field, the transmission decreases because you get more and more spins along other directions which absorb the transmitted light. What you can do also, instead of measuring the absorption on the pumping light field, you can have a transverse weak auxiliary probe, and you look at the absorption at right angle along the OY direction. If you are in zero magnetic field, the spins are pumped along X, and the probability to be in plus and minus state along Y is the same, is equal to, is the same. And so in this case, you don't have any, you have a large, you don't have any absorption of the light along this direction because you have as many atoms which absorb as atoms which are in the opposite direction. So you see that in zero field, you get a signal which is just zero. But if you depart from zero field, you see that the spins start to precess, and you have, for one direction of the magnetic field, you increase the probability of transmission of light along the weak direction. And for the other direction of the magnetic field, you get an increase in the other direction. So what you see is that now the resonance has a dispersion shape. It's like an S shape. And you see that you have a very large slope between a very small negative and very small positive field. So you see that this resonance is very sensitive to very small variation of the magnetic field B0 around zero. I showed on this transparency all the equation of all the block equation which allow you to do the calculation. And I don't want to enter into the details, but I just want to show you that by very simple equation, you can understand what I have tried to explain just with words. It's a very simple experiment. There is no radio frequency. You just look at the competition between the light which orients the spin in one direction and the Larmor precession which tends to fan out the spin in the X or Y plane. Now I want to address on this slide another question which is a very interesting one. In fact, the experiment I have described so far with a spin 1/2 in the ground state coupled to a spin 1/2 in the excited state are experiments which are performed with nuclear spins. In fact, most of these experiments were performed with mercury, and the mercury in its ground state, there is an isotope of mercury which has a spin 1/2 and a nuclear spin 1/2, and the angular momentum, orbital momentum, and spin, electronic spin are zero. I just remind you here the spectroscopic notation. When you want to qualify an energy level, you have the principal quantum number n, you have S, which describes the total electronic spin, 2s plus 1 measures the spin degeneracy, L, which can take the value 0, 1, 2, 3, 4, is the orbital momentum of the electrons. And then you combine L and S to get the total angular momentum, which is L plus S. And in the case where you have a nuclear spin, you have to combine the electronic angular momentum J with I to get the total angular momentum F. And in the case of mercury atoms, F is equal to 1/2, and it's just a nuclear spin. And the optical pumping is just obtained when you pump the atoms on the m equal 1/2 in the ground state towards the m equal plus 1, according to this process, absorption of light and re-emission of light. Now, the question I am asking is, how is it possible that the nuclear spin get oriented? In fact, the light interacts with the atoms through its electric field. It's an electric dipole transition. The light induced an electric dipole on the electron variables, and this coupling transfers angular momentum from light to electrons. And so how does the nuclei get oriented? In fact, they get oriented because in the excited state, there is a coupling between the electron and the nuclei. You see that, in fact, the excited state, in the case of the transition I am studying, it has two hyperfine levels. You combine the spin 1, the angular momentum 1, with the nuclear spin 1/2, and you can get either F equal 1/2 or F equal 3/2. And you have this, what is called a hyperfine separation. Now, the light which we use for optical pumping, as I explained to you in the previous lecture, is made of trains of light, very short trains of light, which are incoherent with each other. And each train of light has a spectral width delta, which I show you here. And delta is small compared to the hyperfine structure because we want to excite only this state and not the F equals 3/2 state. So we have very narrow spectral excitation. And according to Fourier transform, a narrow line in terms of frequency means that it is a light pulse which lasts a long time in the time domain. And in fact, during the time that the light is exciting the atom, there is a time for the coupling to occur between the nuclear spin and the electronic spin. So this coupling occurs during the process of light absorption because of the coupling, the hyperfine coupling between the electron and the nuclear. And when the atom comes back to the ground state, the orientation remains on the nucleus. There is no longer any orbital angular momentum. All the orientation is in the nuclear spin. On the right part of the slide, I analyze another process which is very interesting and which occurs in helium. And I look at the case of helium-3. The helium-3 atom has, in fact, its nucleus is made of 2 protons and 1 neutron, and it has a spin 1/2. So helium-3 has a spin 1/2 in the ground state. And I have shown to you here the spectrum of helium. There is a ground state, which has an L equals 0 orbital. That is, the electron occupies a spherical orbital with same probability for the electron to be in any direction. And in the middle of this orbital, on the nucleus, you have a spin 1/2, which is, so to speak, protected from outside by this electron cloud. And then the first excited state in helium is shown on the right part of this diagram. It's called the two triplet S1 state. It is a state which has a lot of energy, about 20 electron volt. It has a total electronic spin equal to 1 because the two electronic spins are parallel. 2 spin 1/2 parallel gives a spin equal to 1. And the total orbital momentum is 0. So when you combine 0 with 1, you find a J equal to 1, and a total electronic angular momentum equal to 1. And when you combine this total angular momentum equal to 1 with the nuclear spin equal to 1/2, you get an F equal 1/2 state and an F equal 3/2 state too. But I look here at the F equal 1/2 state, which has the same symmetry as in the case of Mercury. And so by using a circularly polarized light, which excites 2s to 2p, and this light is light around 1 micron of wavelength, you orient the electronic orbital in the 2,3s1 state. And by exchange between the orbital and the nuclear spin, you orient this F equal 1/2 state exactly like in the case of Mercury. But what we want is to orient the helium-3 in the ground state. And for that, we take advantage of collisions between the two triplet S1 state and the one singlet S0 state. When two atoms collide, in fact, what can happen is that the orbital electronic configuration jumps from one atom to the other. And during this process, which takes a very short time, the nuclear spin is not affected. So you end up, if you have a collision between an A atom in the metastable state and a B atom in the ground state, after the collision, you have the A atom, which is now in the ground state with its spin oriented, and the B atom in the triplet S1 state. So by this process, you can first orient the nuclei in the metastable state and then transfer this orientation in the ground state. And once the ground state is oriented, you can just cut off the excitation by electric discharge, which excites these atoms, and get a very long lasting orientation of the helium nuclei in the ground state. And this is a feature which is used in a lot of magnetic resonance experiments. Now, I will also describe another experiment which I did during my thesis, which is the optical pumping of rubidium atoms. Rubidium atoms have a structure, hyperfine structure, which I show you here. The ground state is F equal 1. The first excited at F equal 2. You pump from F equal 1 to an excited state, and the atoms come back to the ground state by spontaneous emission. And what you see is a process which I show you here. In red, you see the transition which go from the ground state to excited state, increasing the angular momentum because I pump with circularly polarized photon. And spontaneous emission occurs mainly with delta M equals 0 transition, not completely, but mainly. So you see that after a few cycles, the atoms are pumped into the extreme state with angular momentum M equals 3/2 in this case, M equal 2, excuse me, in this state, and they are pumped in the upper state of the hyperfine transition. So you see that the pumping is doing two things at the same time. It's invert the population because you get more atoms in the excited state than in the ground state, and it orients the electronic spin along its direction. Now, this spin is an electronic spin because you see it's a spin which connects levels which have, in fact, different values of f. So it's an electronic spin which has an electronic part, because you see that what you couple is a spin, electronic spin 1/2 with a nuclear spin which is 3/2. So when you couple an electronic spin 1/2 with a nuclear spin 3/2, you get f equal 2 and f equal 1. And so when you orient the system in f equal 2, you have some electronic magnetization. And the electronic magnetization is much more sensitive to magnetic field than the nuclear one, because you have the Q over 2m factor for the gyromagnetic ratio. The gyromagnetic ratio of an electron is about several thousand times larger than the gyromagnetic ratio of a nucleus. And so these transitions are now much more sensitive to magnetic fields. And I show you here the kind of Handler effect that you get in dispersion when you scan the magnetic field around 0 value by pumping the atoms transversely to the magnetic field. And you see a very sharp dispersion curve with a very big, very high slope here. It means that if you are around 0 field and if you change the magnetic field by a very small amount, the signal changes and you are sensitive to very, very small variation of the static field. In fact, this magnetometer, because it's what it is called, is sensitive to about 3 times 10⁻⁻10 Gauss. And this was an experiment that I did also during my thesis in 1969. I did another experiment, which I show you here, which is a double optical pumping experiment. We have 2 cells. One cell, which is shown here in red, where we optically pump helium nuclei, and we pump them along the horizontal direction. And these nuclei, the magnetic moment of these nuclei, create a very small magnetic field on the cell, which is just side by side, which contain rubidium, and the blue cell is the magnetometer. And what we do once we have oriented the helium-3 is to apply a small magnetic field B0, which makes the spin precess in the horizontal plane here. And the precession of the nuclear spin modulates the magnetic field seen by the rubidium atoms. And you see this in the absorption of this probe beam. And you see here the kind of signals that you can detect. On this recording here, you see hundreds of oscillations. In fact, the field is very small. The Larmor precession period is about 90 seconds. And so you see the nuclear spin going slowly up and down along the horizontal direction and detected by the rubidium atoms. So this experiment, which allowed us to observe the nuclear orientation of helium for more than 10 hours, demonstrates the high sensitivity of the rubidium magnetometer and the long lifetime of the helium-3 nuclear orientation. And in fact, since then, this long lifetime of helium-3 has been used in medical applications. What physicians do is that to orient by optical pumping helium-3, and this helium-3 can remain oriented for several hours. You can bring it to hospital and have this helium-3 inhaled by a patient. So the helium-3 fills the lungs of the patient, and then you do magnetic resonance on these lungs, and you can observe with a high contrast the cavities that you have in your lungs, the small cells which are filled with air, and in this case with helium. And this provides information which is complementary from what you can get with usual magnetic resonance imaging. Now, the last thing I want to tell you about this physics of optical pumping experiment performed in the 1960s is a very interesting experiment which was performed by my thesis advisor, Claude Cohen-Tanucci, in 1961 during his own thesis work. He discovered, in fact, the light shift effect, the fact that a non-resonant light a light which cannot absorb photon, which cannot be absorbed by atoms because the frequency of the light does not correspond to a transition frequency in the atom. This light has nevertheless an effect on the atomic levels and can shift slightly the energy levels of the atom. That's why it's called a light shift, by an amount which is proportional to the light intensity. So it's an effect which looks like the lamp shift, except that the lamp shift is due to the vacuum fluctuations. And here it's an effect which is due to photons which are applied to the system. If the light frequency is close to an atomic transition, the shift is inversely proportional to the frequency detuning. So if you get closer and closer to resonance, you get a larger and larger shift, but the shift vanishes at resonance. So it's a dispersive effect. And I will come back to the theory of this light shift later on. But here I just want to show you what is the optical pumping experiment, which has allowed Claude Cohen-Tanuji to observe this light shift for the first time. So it's a magnetic resonance experiment. You pump the atom with circularly polarized light along the direction of the magnetic field, and you apply in the perpendicular direction a radio frequency field. And when omega naught is equal to omega, you get a resonance. But then what Cohen-Tanuji did was to add an off-resonant light beam, a beam which cannot be absorbed, but which produces a light shift effect. And you see this off-resonant light beam can be polarized either in sigma plus or in sigma minus. And look at what happens. If the light shifting field is sigma plus polarized, it can only couple the m equal minus 1/2 state to the excited state. So only this state is affected by the light shift. And in case of red detuning, if the frequency of the light is smaller than the transition frequency, theory shows that the energy level is going down. So the light shift is negative. Now, if you look at the magnetic resonance between the two m equal minus 1/2 and m equal plus 1/2 state, you see that the light shift increases the difference of energy between these states. And so it increases the resonant frequency that you need for the for the radio frequency field. On the other hand, if you excite with off-resonant light sigma minus polarized, it is the other state which is affected, and you see that it will shifted down, and now the distance between the m equal minus 1/2 and m plus 1/2 state is reduced, so the frequency of the microwaves that you have to apply to induce the transition is decreased. So in sigma plus, you have to increase the frequency. In sigma minus, you have to decrease it. And you see the observation that Claude Cohen-Tanuji did. Without non-resonant light, you get a resonance here. And if you apply a sigma plus or a sigma minus light shifting beam, you get two lines which are shifted in one direction or in the other. If you look now at the orders of magnitude, these light shifts are really tiny. It's about 1/2 hertz, 1 hertz, because they're induced by weak classical lamps. This was before the lasers. Now, with laser light, you can induce light shifts which are billions of times larger, which are gigahertz or even bigger. And these light shifts, which completely change the position of the energy levels in the atom, play a very important role in the physics of cooling and trapping of atoms, and I will talk about that in lecture 11. Since I finished describing you the experiments that we performed at around this time in the 60s, I show you this picture, which was taken in October 1966 when Kastler received his Nobel Prize for the discovery of optical pumping. And you see on the picture, you have Kastler and Brossel here, and this is Cohen-Tanuji, and this is me. So you see that it was a long time ago, and I remember it was a very, very nice event in the lab, and I was really amazed. I was a young student at that time, and I was really very much excited by the fact that I had the luck to fall into a lab which had done this research, which had been recognized on that occasion by this very high recognition, this very high award. Claude Cohen-Tanuji received the Nobel Prize something like 30 years later for his work in laser cooling and trapping of atoms. And you see he was about 30 years old. At the time, he was my thesis advisor. So now I will shift gears and talk about the laser and the beginning of nonlinear optics. So the connection with laser is quite obvious. The development of magnetic resonance experiment opened new perspective in the field of light-matter interaction studies. First of all, before this experiment I described to you, matter was prepared out of thermal equilibrium by Stern-Gerlach devices, which required atomic beams, gradients of magnetic field, which were not so easy to manipulate. Now, with optical pumping technique, you can orient, change the population difference by optical means, which is much simpler. And you can invert population, which promised to realize the amplification of radiation that Einstein had predicted in 1916. What also another thing that the magnetic resonance experiment did is to show that one can observe nonlinear effects in matter radiation interaction. Saturation of the atomic response, which is, for example, the reversal of the Majorana transition, Majorana resonance. You can have multiple photon transitions, as I showed to you in one of the slides. And this new domain blossomed with the laser. The nonlinear effects that you observe with magnetic resonance become even more spectacular when you observe them with the light of a laser. So I will briefly review these properties in the remainder of this lecture. I will start by recalling the principle of the maser-laser operation. Then I will briefly introduce the main properties of this new source of radiation, whose performances have been steadily increased over the last 60 years. So I have prepared I have shown you on the slide all the calculations which are required to understand the effect. And instead of going into the details of the calculation, I will try to give you the flavor, the physical content of the equation and what is happening. Let me start with a maser. And on this slide, I show a very simple model of a maser. We assume that we have a cavity, for example, a cylindrical cavity, which sustains a mode of the electromagnetic field, which is resonant with an atom which has or a molecule which has two levels separated by a frequency, Bohr frequency corresponding to a microwave transition. And we assume that there is an electric dipole matrix element between these two states. So they are strongly coupled to microwaves. And we send a beam of atoms across the cavity. The atoms are prepared in the upper state of the transition to have amplification of radiation. And you have a flux of atoms, which I call N0. N0 is the number of atoms entering in the cavity per second. And when the atom leaves the cavity, some atoms are in the lower state, some remain in the upper state. So some photons have been delivered by the atoms to the cavity. So I will assume for simplicity that the field is spatially uniform in the cavity. And there is a mode of the field which is like that. And the field has an amplitude E, and that all atoms have the same velocity, which means that they cross the cavity in the time of flight t0, which is a time corresponding to 1,000 or a few thousands of a second. So now we have to compute two competing effects. First, the energy which is brought per second by the flux of atoms which cross the cavity. And this flux is very simple to compute. I call delta plus W the energy which is delivered to the cavity per second. It's proportional to the number of atoms which cross the cavity per second, to the energy of each photon, h bar omega, and to the probability that the atom will go from the upper to the lower state during time t0. And since it is a coherent process, since the field which is building in the cavity is a sine wave, you see that we can apply the Rabi formula. The probability for the atoms to go from the upper to the lower state is just sine square of the Rabi frequency dE over h bar time t0 over 2. And you see that at short times, this quantity of energy is proportional to E square. Sine square d t0 over 2h is proportional to E square. Now, what is the loss? The cavity loses energy because the cavity walls are not perfect. And what you need to have is a parameter which is called the Q factor of the cavity. The Q factor is a big number, which represents the number of periods that the field can evolve into before the field is lost. So Q is a huge number, and omega over Q is something which is proportional to a rate. It is a rate of losses of the field, and the quantity of the field loss is equal to the energy in the cavity, which is epsilon naught E square V, where V is the cavity volume, time over omega over Q. And if you want to have in steady state operation of the maser, you need to have delta minus W equal delta plus W equal to delta minus W. In this case, the losses are equal to the gain, and you have a steady state operation. So I show you here what happens below threshold. If you have below threshold, the sine curve, sine square, T0 over 2h bar, which is given by this curve, has a slope at origin, which is the red slope, which I show here. And the losses, which are proportional to E square, are given by the blue line. And you see that below threshold, the losses at origin are larger than the gain. So the system cannot start oscillating. If you have some noise in the cavity due to spontaneous emission, the field is brought back to zero because the losses are larger than the gain. On the other hand, if you are above threshold, you see the situation here, the Rabi oscillation is much bigger, and the slope at the origin of the gain variation is larger than the losses, and you see that the system will start and it will stabilize at this point where the gain is equal to the losses. So it's very simple. I just show you here the formulas which express the fact that the gain is larger than the losses. And if you put the figures that you have in a standard maser, a volume of about 10⁻³ cubic meter, a time of about 1 millisecond to cross the cavity, a Q factor of the order of 10 to the 5, and an electric dipole, which is of the order of QA0, what you find is that the flux of atoms that you need to have across the cavity is of the order of 410 to the 11. So you need hundreds of billions of atoms crossing the cavity per second to reach the threshold condition. And this is what has been obtained by Towns and Gordon with the ammonia beam maser back in 1954. So as soon, and you see what is important in this process, what is important to find the operation point is the non-linearity of the gain. You see, if the gain was linear, the gain would follow this red curve indefinitely. But in fact, it curves and it goes down because of a non-linearity, the fact that the response of the atom cannot follow the electric field proportionally to the score of the electric field. There is a moment due to the finite value of the electric dipole that you have saturation of the probability of transition, and this saturation is essential to find the operating point of the maser. And the same thing happens if you go to the laser. And so in the next 2 or 3 slides, I will give you a simple model of laser. And I first remind you about linear optics, which is something that a point which I evoked when in the 3rd lecture or in the 2nd lecture, when I talked about Maxwell's equation. But we have to take into account that in a laser, the field is evolving. The field depends on time and position. For example, in a laser cavity, you have a field which is a plane wave going in one direction and the other. And in order to understand how the field propagates, you have to take into account the fact that the atoms correspond to a microscopic current in the cavity. And I have tried to explain you this here. First of all, you have to compute the density of atomic dipoles, how many dipoles you have per unit volume. So it depends on the number of atoms per unit volume. You have to multiply this by the electron charge and by the microscopic separation which you have in each atom between the nuclei and the electron, which I call R bound, the distance of an electron bound to a nucleus. And when you apply an electric field to the atom, you separate with the electric field the center of gravity of the positive and negative charges, and you get a non-zero value for R bound, which is proportional to the electric field at the lowest order. And so you have a microscopic current of bound charges that you can write in this way, n number of particles per unit volume, Q, which is the electron charge, and the derivative of R bound over dt, which gives the microscopic current. And this quantity is just dp over dt. So then you can introduce this microscopic current into the Maxwell Ampere equation. I remind you that the curl of B is equal to mu naught J, where J is here, J bound here, plus the displacement term that Maxwell added to the current, E0 dE over dt. So this is a Maxwell equation, which adds now this red term in red, which takes into account the fact that the electric field drives the electrons inside the atoms and produce this microscopic current, which is distributed in the volume. And as we did in lecture 2, we can eliminate B with the help of the Maxwell-Faraday equation, and we get, for the propagation along OZ of the plane wave, polarized along OX, a new form of the D'Alembert equation. You see this term, d squared over dz squared of EX minus 1 over c squared d squared over dt squared. This term is a D'Alembert term which describes the propagation in free space. And you have an extra term which is written here, which is produced by the atoms excited by the field. This is a source term, if you want, which feeds the electromagnetic field in the cavity. And so you have to solve this equation. And in the linear approximation, what you assume is that P is just proportional to E. P is equal to epsilon naught chi of omega times E of omega. Chi of omega is called the linear response. It's the proportionality between the applied field and the polarization. And it's a quantity which depends on frequency. So it's a function chi of omega. And it's a quantity which has a real part and an imaginary part. And so when you separate the real part, which I call chi prime, and the imaginary part, which I call chi double prime, you find that the wave vector of the field propagating in the medium is now omega over c. This is the term you have in vacuum, minus chi omega over 2, minus I chi double prime omega over 2. And you can write it in the form written here. The real part of the susceptibility is just the refractive index, which describes how the phase velocity of the light in the medium is modified from what it is in the vacuum. So instead of c, we get c over n. And the imaginary part gives the length over which the field will be absorbed or amplified. And in the case of ordinary optics, chi double prime is a positive quantity, which means that the field is absorbed and that the field is decreasing with a characteristic length L omega, which is minus c over omega chi double prime of omega. So this is just linear optics. And you see that this is a result which I had already discussed in the second lecture, the fact that the real part of the index, which is in phase, which corresponds to the part of the polarization which is in phase with the applied field, gives rise to the index effect. And the part which is in quadrature, which is pi over 2 out of phase with the applied field, describes the attenuation of the field along the medium. Now, if you want to have amplification and laser action, you have to change the sign of chi double prime. Chi double prime has to become negative instead of being positive. And in this case, you will have amplification instead of having attenuation. The medium will amplify light by stimulated emission if chi double prime of omega is negative. And this requires, of course, a population inversion. And so I have written here how in the regime of linear optics with a negative chi double prime, how does the field evolve in the cavity? Instead of decreasing exponentially, the field will increase exponentially. And you will have dE over dZ, which will be equal to a positive quantity times E. This is a one term here. So you will have an exponential amplification of the field in the cavity. And this corresponds to the linear departure in the case of the maser, the fact that you have an amplification proportional to the light intensity. But of course, this cannot last forever, because if the field increases, there is a point where saturation effects will take over. And saturation effects means that the linear response will be moderated by a negative term, 1 minus I naught over IS, where I naught is the typical saturation power. IS is a typical saturation power. So when I naught is small compared to IS, you have an exponential buildup. And when I naught becomes of the order of IS, you have a saturation. And you can express this in terms of the intensity, the square of E, and you get this expression. You see that the field is amplified over a typical length, which is here negative, so it gives a positive exponential with a saturation term here. on the next slide, I write the saturation term in a different way. Instead of writing 1 minus I naught over IS, I write it as 1 over I plus I also I naught over IS. And if you develop this, you find that the first term, the term that I showed on the previous slide. But this expression is something which reminds us of the saturation of magnetic resonance that I discussed last week. You see that the saturation is expressed in a more proper way by just limiting the effect of amplification by this factor. The larger is I naught, the smaller is the gain that you get, the differential gains that you get over the propagation distance. So once you have this formula, you can understand everything what will happen. So this is a sketch of a laser. You have a cavity, so you have a standing wave going back and forth between mirrors separated by distance L. You have an amplifying medium which has a length LA for amplification, and you have two mirrors which close the cavity on both sides. And this mirror is slightly transparent. It has a reflection coefficient R and a transmission T equal 1 minus R, where R is very close to 1. And the equations are shown here. You can compute the gain in a round trip. Di over I is given by the expression that I've shown you here. And you have the losses in a round trip, di over I. The losses is just 1 minus R. Each time the system makes a round trip, a fraction 1 minus R is going out, so this is a loss. And when you equate the gain and the losses, you get this expression, which you can retrieve by yourself. And you see that the steady state amplitude of the laser is given by this formula, and it implies the imaginary part of the linear response, chi double prime 1, with this factor instead in front, and you have here I as the saturation power. So the steady state operation depends on saturating power of the medium and depends on chi second 1. So I let you compute this. And after a few lines of calculation, you find very easily that the condition for threshold is to have minus chi double prime 1, which is the linear amplification, has to be larger than typically than 1 over Q, where Q is the quality factor of the cavity. Q is the number of cycles that the field can evolve into before damping occurs. And so you need to have a very good cavity, a very large Q, and minus chi double prime 1 has to be larger than 1 over Q times this dimensionless factor, which is the length of the cavity divided by the length of the amplifying medium. And you see here how the intensity varies with minus chi double prime 1, what happens if you have minus chi double prime 1 smaller than this condition. The laser is below threshold, and above threshold, the intensity of the laser increases proportionally to minus chi double prime 1. So you have a variation with a threshold, and then you have the laser action taking place. And here I have just given orders of magnitude. You see that what you need to have is a linear amplification, which is of the order of the difference of population between the excited and the ground state, that is population inversion, times the square of the dipole, and this has to be larger than 1 over Q times L over LA. And when you look at the orders of magnitude, you find again that you need billions of atoms in the cavity to reach the condition for the gain to be over the losses. So I think I will stop at this point, and we'll stop for 10 minutes, and I will resume in 10 minutes from now.